Alright, so this is when we're going to start talking about one-dimensional kinematics as we begin our unit on kinematics and vectors. So one thing to remember about one-dimensional kinematics is that we get a set of four equations that describe the motions of objects, and these work only under the situation where acceleration is constant. And for one-dimensional kinematics, you only have one dimension of motion, meaning it's forwards and backwards, up and down, or side to side. And you get four equations which describe position, velocity, initial velocity, acceleration, and time. And here are the four equations. I usually refer to these as the toolbox equations. You can take some time and derive some of these if you want. Some of them come out of other definitions. This one, the definition of acceleration. This one using the definition of average velocity. This one you can get two or three different ways. And this one you can get two or three different ways depending upon how you actually want to go about deriving those formulas. So let's do some example problems of these formulas. What I find with one-dimensional kinematics is that lots of times the example problems are fairly straightforward. They might be a little bit algebra intensive, but you ultimately end up with an equation that you plug all the numbers in and get one value. So here we have a red car which is sitting at rest at a stoplight, and the moment the light turns green, the red car is passed by a blue car that moves at a constant velocity. The red car is going to accelerate with a constant acceleration, and I want to know two different questions. How much time elapses before the red car catches up to the blue car, and how far have the cars traveled from the stoplight during that time period? So here's the situation we have. If we collect all the things that we know about this situation, we know the initial velocity of the red car is 0, the initial velocity of the blue car is 20, we know the acceleration of the red car is 4, we don't know the final velocity of the red car. We do know the final velocity of the blue car, that it's also 20 because its acceleration is 0. So the velocity of the blue car is always 20. And we don't know x or t about this system. So what I can do to describe the relationship of x and t for both of these different cars is I can really modify that third toolbox equation, v initial t plus 1/2 at squared. And so here's for the red car, v initial t plus 1/2 at squared, and here's for the blue car, v initial t. Since I know it's constant velocity, a must be 0. Now I am going to simplify the red car equation because I know it starts at initial velocity 0, so that first term is 0. So x is equal to 1/2 at squared. So at this point, I have two equations, two unknowns. This is what we call a system of equations, and it's possible to solve this system for one of the unknowns and then plug it back in to find the other unknown. The nice thing about both these equations is they're both solved for x. So let's set 1/2 ar t squared to vbt, and I can solve that for t ultimately. Divide both sides by a t, multiply by 2, divide by ar, and then if we plug that in, we get that t is equal to 10 seconds. So it takes 10 seconds. So here there's one of two ways that I could do this. I could either plug t back into the blue car equation, 20 times 10 equals 200, or I could plug t back into this equation, 1/2 times 4 is 2, times 10 squared 100, 2 times 100 is also 200. So either way you get the same answer. So this is an example of what I call a shared variable problem. We have two things moving at once and trying to figure out what's happening with both those objects. The second type of situation that I want to deal with, it's a one-dimensional kinematic situation that we see quite frequently, is what we call free fall. And free fall is where the acceleration is only due to gravity. This is when an object is falling under the influence of gravity. It's said to be in free fall if it's falling only under the influence of gravity. So if we ignore air resistance, acceleration of gravity near the Earth's surface is about 9.8 meters per second squared in the downward direction toward the surface of the Earth. And that's true for actually quite a ways. When we talk about near the Earth's surface, it's actually true for quite a ways above the Earth's surface. If you measure the acceleration of gravity due to the Earth, even at the International Space Station, which is something like, about 60 to 90, I think it's like 90 miles above the surface of the Earth, it's still about 9.8 meters per second squared. It's a little bit less, but not significantly less. We'll get into that a little bit later when we talk about the motion of satellites and rockets and things like that, and later on in this term. So what does no air resistance, or when does this assumption actually work? So we're making a big assumption here, ignore air resistance. And there's a few situations where this there's a few things that must be true for this assumption to work. This works well for objects that move at relatively low speeds. Speeds like 10 meters per second are relatively slow speed. If you have things that are moving at, say, 5,000 meters per second, air resistance almost always is a big deal for that type of object. So you look at something like me throwing a tennis ball across the room versus me shooting a bullet across the room. Those are two very different situations. The tennis ball, probably this no air resistance assumption works pretty well. Depending upon the type of bullet, this may work well or it may not work well. Objects that tend to have a large amount of mass tend to experience a smaller proportion of air resistance. Basically, gravity is a stronger force for those, and air resistance generally is related to surface area and speed. Objects with smaller amounts of surface area tend to have less air resistance, and so the things you want to look for is objects that are relatively large in mass, small amount of surface area, relatively slow speeds. Most of the situations that we encounter in the lab, air resistance is negligible, meaning that it is so small that it can be ignored in most situations that we deal with in the lab. So let's use an example. Let's say we have Susan, she's going to stand at the top of a 50-meter tall tower and going to drop a ball. At the same time she drops the ball, Bob, who is halfway up the tower, is going to throw his ball straight up into the air. The question is, how fast does Bob have to throw his ball so they both land at the bottom at the same time? So this is a pretty complicated problem. This is kind of like our blue car, red car problem is a two objects moving at the same time shared variable type problem. So if we look about what we know first of all that the acceleration of both the balls after they're thrown or dropped is negative 9.8, calling negative the downward direction. We know the initial velocity of the top ball, the one Susan has, that I'm going to label with an S, is 0 meters per second. I know the height that Susan's ball is going to fall is 50 meters. Height that Bob's ball has to fall ultimately is 25 meters. This is the displacement of the ball, not its actual distance traveled. I'll point that out. So some unknown things: we don't know the time of travel. We don't know the final velocities of either ball. There's nothing to suggest the final velocities are going to be the same. We know if they hit the ground at the same time, the time must be the same. This is ultimately the variable we want to calculate here. How long does it take for them to hit the ground? We also don't know the initial, we want to define the initial velocity of Bob's ball so that this was true. So this is kind of a constraint we're putting on the system. So let's look at some relationships. We could define Susan's ball by this equation, half gt squared. We can define Bob's ball by v0bt plus a half gt squared. So let's do some algebra. So the very first thing I can do is I can calculate what t has to be, because we know what t has to be, or at least we can calculate it from Susan's ball equation. Square root of 2ys over g. How long does it take for Susan's ball to fall? We can plug that in now for t, and we get an equation that looks like this, that yb equals v0b times the square root of 2ys over g plus half g 2ys over g, because we squared the square root. Here some things cancel, the half and the g cancel, and so you ultimately end up with is a v0b square root of 2ys over g plus ys, which we can solve for v0b. The way to do this is subtract ys from both sides and divide it by the square root of 2ys over g, or multiply by the square root of g over 2ys. I flipped the radical. Your math teachers would really like that because I've made this look nice and pretty for them. Math teachers generally don't like radicals on the bottom of fractions. This takes care of that. So here what I've done is I've solved this problem all symbolically. I would definitely get in the habit of doing this in this course, because you will run into problems where you don't know what ys and yb are, and you're supposed to find what is v0b in terms of ys and yb. And so you're going to have to do this type of thing, and you've solved the problem at this point. We can then solve it out numerically, plugging in the values, and you get that Bob has to throw it 7.83 meters per second straight up in the air in order for this to be true. So that's kind of our quick overview of 1D kinematics. The two problems that I picked are, well, not simple plug and chug problems. They require a little bit of work. You'll see some of the problems you come across, or the problems I'm going to pick probably require a little bit more work than the simple plug and chug, find the numbers, plug them into an equation, solve the equation. So that concludes our lesson on 1D kinematics. What we'll do kind of in the next lesson is start looking at vectors and scalars in a little bit more detail.